James Webb doesn't orbit Earth. It orbits a spot of empty space 1.5 million kilometers away. How can you orbit nothing? Webb sits near the Sun Earth L2 Lagrange point, about 4 times farther than the Moon. From there, a radio command takes roughly 5 seconds to arrive, and a $10 billion telescope stays aligned so the Sun is always behind its sunshield. No fuel burned, no thrust, just gravity. The weird part is the phrase, orbits a point, because there's no planet at L2 pulling it around. So what is actually being balanced at that location, and why doesn't Webb simply drift off within days? And the answer is that Webb isn't orbiting nothing. It's orbiting the Sun with Earth, and Earth's gravity tweaks the motion. L2 sits about 1.5 million kilometers beyond Earth, so Webb is about 1% farther from the Sun than we are. At that larger radius, a free object would naturally take longer than a year to orbit and would fall behind. But Webb stays almost lined up with Earth, so it must go around the Sun once per year anyway. To curve that fast at that distance, it needs a bit more inward acceleration than Sun gravity at that range can provide. Earth supplies that missing few percent, pulling Webb slightly sunward. If you switch to a reference frame that rotates with Earth's yearly orbit, the combined Sun plus Earth gravity and the outward centrifugal tendency balance at special locations. Those are Lagrange points. So why choose L2 as a home base instead of a normal Earth orbit? Because L2 is a geometry trick that buys you a remarkably clean observing environment. Near Earth, you get rapid heating and cooling every 90 minutes, earthshine in your instruments, and frequent eclipses that interrupt power and observing. At L2, the Sun, Earth, and Moon stay bunched together in the same direction, so Webb can keep one sunshield permanently facing them while the telescope looks out into deep space. That lets the optics sit around 40 Kelvin, cold enough to see faint infrared signals, from the first galaxies to the chemical fingerprints in exoplanet atmospheres. And L2 is close enough for constant contact. 1.5 million kilometers is only a 5-second radio delay. Stepping back, this is why so many astronomy missions, Gaia, Euclid, Webb, go to L2. But if L2 is a balance point, why does every spacecraft there still carry fuel? Because L2 is balanced like a pencil on its tip. Perfectly possible, but not self-correcting. A tiny push from sunlight pressure, a small navigation error, even gas venting from the spacecraft changes the orbit, and the dynamics amplify the drift. So, missions do station keeping, brief thruster firings that add up to only a couple of meters per second of speed change per year, to stay nearby. And they don't sit exactly on the point. They fly a halo orbit, a slow, 3-dimensional loop around L2, typically hundreds of thousands of kilometers wide, with a period of a few months. That loop keeps solar panels lit, avoids long eclipses by Earth, and keeps Earth continuously in view for antennas. So L2 isn't a parking space, it's a region you patrol. The lingering mystery is, why does being a little off balance make you drift even farther off? The instability comes from feedback between distance, orbital period, and the rapidly changing pull of Earth. At L2, Earth is only 1.5 million kilometers away, so shifting by 100,000 kilometers, less than a third of the Earth-Moon distance, changes Earth's gravity by around 15%. Imagine Webb drifts a little sunward, closer to Earth. Earth's tug strengthens, adding extra inward pull toward the Sun. That nudges Webb into a slightly smaller, faster solar orbit, so it creeps ahead of Earth, and the alignment that defined L2 gets worse. Drift grows. If Webb drifts outward, Earth's tug weakens. Webb can't keep that one-year pace at its larger radius, and it falls behind, again increasing the mismatch. In a rotating frame, that's why L2 is a saddle point, stable in some directions, unstable in one. Like a mountain pass, you don't roll back to the middle. A small displacement changes the balance between gravity and the needed turning rate, so acceleration points away from the point. Station keeping burns are just timed nudges that cancel that runaway drift before it becomes a full escape. So, if the point itself can't hold you, in what sense is Webb orbiting L2 at all? You orbit nothing by sharing Earth's one-year solar orbit, with gravity and rotation balancing near L2. From the Sun's point of view, Webb is simply in a solar orbit a little farther out than Earth, with Earth's gravity giving it a gentle, extra inward pull. From Earth's point of view, that same motion looks like a spacecraft hovering in deep space, always near the anti-sunward direction. Stepping back, that's the power of choosing the right reference frame. A tricky three-body dance turns into a usable piece of celestial real estate, and we're already building around it. Next-generation observatories, deep space communication hubs, even relays near the Earth-Moon L2 to reach the lunar far side. Orbiting nothing isn't magic. It's geometry plus careful nudges. Like if this was interesting, hit the subscribe for more and turn that notification bell on.